This video is on section 4.4 about discrete probability. So we'll give some definitions and examples and some applications, and then we'll also talk about something called expected value. We define probability in terms of sizes of sets. So we start with a set U, a finite set. So let's suppose this is U. And then we choose a subset, A of U. So maybe this is A in here. Then the probability that a randomly chosen element of U lies in A is the ratio of the size of A to the size of U. So when we say the size of A, we mean the number of elements of A. The size of U is the number of elements of U. So with the set U is called the sample space, and the set A is called an event. Okay, so let's compute a probability. So let's suppose you get a random license plate from all the possible Illinois license plates described above. So we'll talk about what that means in a moment. What is the probability that your plate contains the word cub or the word socks? Okay, so first of all, let me remind you about how Illinois plates were described above. So remember, there were two possibilities. The first possibility is that there are three letters followed by three digits. The other possibility is that there were two letters followed by four digits. And in a previous video, we discovered that the number of such plates is 24,336,000. So that's our sample space, this collection of license plates, and the size of that sample space is 24,336,000. Now, in that sample space, we're looking at the event that a plate contains the words cub or socks. So whatever plates those are, they don't come from here, right? Because there are only two letters in that type of license plate. And so what we're looking for is this type of license plate. So let's suppose we have the word cub here. How many ways can that happen? Well, the letters have been completely determined, but there are still three digits that could be anything there. And each digit slot can be filled in 10 ways. So that means that there are 1,000 ways that those last three digits could be filled. Now, the same thing is true for socks, right? If we replace the word cub with socks, then again, we have 1,000 ways that we can complete that plate. So the size of the set A, that is the set of plates that have the words cub or socks, is 1,000 plus 1,000. Okay, so that fraction reduces to about 1 over 12,000, which is this very small number. So it's very, very unlikely that your randomly generated plate will have the word cub or the word socks. Okay, here's another example of probability. So let's suppose we have two standard six-sided dice, and in fact, we're going to identify them as dice 1 and dice 2. What is the probability that you roll an 8? That is, that the sum of the values on the two dice will be equal to 8. So the sample space is the collection of all possible rolls, right? And those can be expressed as ordered pairs, A comma B, where A is the roll from dice 1 and B is the roll from dice 2. So there are 36 possible ordered pairs of that form. And what we want to do is identify the ordered pairs where the sum of each entry in the pair, the sum of the two entries in each pair is equal to 8. So dice 1 could give 2, dice 2 could give 6, dice 1 could give 3, dice 2 could give 5, dice 1 and dice 2 could both give 4, dice 1 could give 5, dice 2 could give 3, and dice 1 could give 6, dice 2 could give 2. Those are all the possibilities. So there are, we count them, there are 1, 2, 3, 4, 5 of these ordered pairs. So the probability of rolling an 8 is 5 divided by 36, which is about 0.139. Okay, sometimes it can be useful to employ the complement of a set and subtract to get a probability. So here, to give you an idea about what we're talking about, let's suppose this is our sample space, this rectangle. And let's suppose this bit here is our subset A. Then that means that A complement is everything in our sample space U that is not in A. So that means that A complement is over here. So observe that that 1 is the probability of U, right? Why is that? That's because the probability of U is just the size of U over itself. But U is equal to A union its complement. But the size of A union its complement is just the size of A plus the size of its complement. That's because A and A complement have nothing in common. And that is the size of A over U, size of U, plus the size of A complement over U. And that is the probability of A plus the probability of A complement. So now if you take this equation, if you look at where we started with 1, and we saw that that was the probability of A plus the probability of A complement. And so what that means is that we have this new formula that says that the probability of A is 1 minus the probability of A complement. Okay, now you might be wondering why this would be useful. Well, sometimes it's easier to compute the probability of A complement than it is the probability of A. So if you're seeking the probability of A, and it's easier to compute the probability of A complement, then this formula could be useful. Okay, here we're going to use the complement probability formula in an example. So here we roll 2 standard 6-sided dice. What is the probability that you roll a 10 or less? Well, here it might be easier to figure out what the probability is of rolling more than 10. So there are only 2 ways to roll an 11, right? You can have a 6 on the first die and a 5 on the second, or a 5 on the first and a 6 on the second. And there's only one way to roll a 12, right? That's double 6s, right? So the probability of rolling more than 10 is 2 plus 1, or 3 out of 36. So that's 1/12. And that means the probability of rolling 10 or less, well, that's the complementary event. So the probability of that is 1 minus 1/12, or 11/12. Okay, here's a probability application, so to speak. So we're starting at A, and the question is, what's the probability that you pass restaurant R on the way to point B? So again, we're going to assume that the only directions that we're going to move are south and east, because it would be counterproductive to move north or west. So what we want to do is just figure out which of the paths. We want to consider all of the paths from A to B, and then we want to consider which of them pass the restaurant R. Okay, so we can use a decision tree for this problem, right? Just as we did in a similar problem earlier in an earlier video. So we have this decision tree that identifies 6 paths that go from A to B, but 4 of those paths go by the restaurant R, right? So it's this path, this path, this path, and this path. And so the probability of passing the restaurant is 4 out of 6, or 2 out of 3. Okay, here's another application. Right, suppose that there are 10 defective machines in a group of 200 machines. A quality control inspector takes a sample of 3 machines and tests them for defects. How likely is it that the inspector discovers a defective machine? So first of all, the sample space is the total number of selections of 3 machines. So that's this C200, 3. Right, that's the total number of selections of 3 machines. Now, instead of considering the event that at least one of the machines is defective, it's easier to consider the opposite event, that none of the machines we select are defective. So there are 190 non-defective machines, and that therefore, if we look at all possible selections of 3, those are the samples that contain no defects whatsoever. So the probability that there is a selection has at least one defective machine is 1 minus the probability that there are no defective machines in the selection. So that's 1 minus C190, 3 divided by C200, 3. And computation gives that probability is about 0.1433. Okay, here's another application of probability sampling. So Rodelio wants to know if a majority of voters in his town will support his candidacy for mayor. And suppose, for the sake of this discussion, that out of 300 voters in this town, 151 support Rodelio. But Rodelio doesn't know this information. Rodelio selects 20 voters at random from the population of 300. What is the probability that out of this random sample, fewer than 5 people support Rodelio? Okay, so the sample space in this instance is the set of all possible random samples of 20. So the size of the sample space is the number of selections of 20 from 300. Now, the event A, that fewer than 5 of the voters in this sample support Rodelio, is this number. All right, so how are we computing this? Well, we've got our 20 people, right? Let's suppose out of these 20 people, 0 of them support Rodelio. Then there are, how many ways can that happen? That means that all 20 are non-supporters. So remember, there are 151 supporters. And because the population is 300, there are 149 non-supporters. So we've got these 20 people, and we're now going to assume that 0 of them are supporters. How many ways can that happen? Well, there are 149 non-supporters, and all 20 of them, we're assuming that we're counting the number of ways to select 20 from these 149. So this is 0 supporters. Now we look at what happens if we have 1 supporter. Well, there's 151 ways to choose that 1 supporter, and then 149 choose 19 ways to choose the 19 non-supporters out of the 20. Now here we're imagining we have 2 supporters. There are 151 choose 2 ways to choose those 2 supporters, and 149 choose 18 to choose the other 18 non-supporters. And then so on and so forth. 151 choose 3 ways to choose 3 supporters, and 149 choose 17 ways to choose the remaining 17 non-supporters. And then finally here we have this product. So when you add all those things together, you get a number which is not given to us here on this slide. But when you compute that number and divide it by the size of U, which is 300 choose 20, you get 0.0042. So you should maybe pause the video and make sure that you're able to obtain that number. Okay, so here we have this interesting question. Let's suppose that Rodelio conducts a poll of a sample of 20 and finds that only 4 supporters support his candidacy. Do you like his chances to win the election? Well, let's imagine that he were capable of winning the election. That is, he had 151 supporters. Then we just saw that the probability of having 5 or few, out of a sample of 20, having 5 or fewer support your candidacy is some really small number. And so if he has 5 or fewer, or say 4 supporters in this group of 20, it doesn't look very good for Rodelio. Okay, so here we're going to talk a little bit about expected value. So first of all, a random variable is an object that can have several different values. For instance, if you flip a coin, that can be considered a random variable because the values of the outcomes can either be heads or tails. So here xn would be equal to 2, x1 could maybe be heads, and x2 would be tails. Okay, so sometimes we're interested in computing what's called the expected value, denoted by e of x, of a random variable x. And the way that you compute it is you multiply each outcome. So we're going to assume that the outcomes are numerical now, not just like heads and tails, but maybe like 0 and 1. So you're going to multiply these numerical outcomes by the probability of that outcome. So that is, and then you're going to add all those things together. So the expected value of x is x1 times the probability that x1 occurs, plus x2 times the probability that x2 occurs, and so on and so forth, until you get the xn times the probability that xn occurs. Okay, here's an example involving expected value. So we've got the both ways version of Australia's Cash 3 lottery, where you pick a 3-digit number from 0 to 999, and a randomly chosen winning 3-digit number is announced every evening at 5:55 p.m. If you pick a number with 3 distinct digits, you win $580 if your number matches the winning number exactly. And you win $80 if the digits of your number match the digits of the winning number, but in a different order. The question is, what is the expected value of the money you win? Okay, here we have an example involving expected value. So our random variable is going to be the amount of money that we win in this lottery game. And remember, the possible outcomes are you win nothing, or you win $580, or you win $80. So out of the 1,000 possible numbers, there's only one that matches the number that you've selected. And there are 5 others that have the same digits as yours, but are in some different order. So your expected winnings are as follows. So we take 0 times the probability of outcome 0, 580 times the probability that you win 580, and 80 times the probability that you win 80. So let's start with the 580 times the probability that you win 580. So the probability that you win 580, that's the probability that the number selected is your number. And that's 1 in 1,000. So we take 580 times 1 over 1,000 to get that middle term. Now then, what's the probability that you win 80? So what's the probability that you win $80? Well, that happens when you're in one of the 5 situations where the number that was selected is your number, but in some different order. And there are 5 ways of that happening out of 1,000 possible numbers. So this probability of winning 80 is 5 over 1,000. So we get that term in the expected value. And then the probability of everything else, anything else happening, right? So we have 1 out of 1,000 here. We have 5 out of 1,000 here. The probability of anything else happening, that is the probability of you losing and winning $0, is the remaining probability, namely 994 over 1,000. And you multiply that by 0. That's the outcome there. So if you add all these terms together, you wind up with this number, $0.98. So the question is, how much would you pay to play this lottery game? Well, if you pay anything more than $0.98, then your expected value becomes negative. So you would want to pay something less than $0.98.